Hello, and welcome to tonight's video lesson on empirical formulas. Empirical formulas are small whole number ratio formulas of the actual molecular formula of compounds. They're very useful in determining the ultimate molecular formula for a particular compound. Let's try an example. A 2.012 gram sample of a compound of nitrogen and oxygen has 0.522 grams of nitrogen. I would like to calculate the empirical formula of this nitrogen and oxygen containing compound. Since they've given us the total mass of the compound sample, and they've only given us the mass of the nitrogen, I have to take by difference to solve for the oxygen. So the first thing I want to do is subtract the 0.522 from the 2.012 grams. So 2.012 grams minus 0.522 grams of the nitrogen. And when I do this, I got 1.49 grams of oxygen. So now I have the gram mass of the oxygen and the gram mass of the nitrogen. Recall that the subscripts in the chemical formula, be it empirical formulas or molecular formulas, are moles. So the next thing we have to do is a gram to mole calculation using the molar mass of the nitrogen and the oxygen. So let's start off with the nitrogen. We have 0.522 grams of nitrogen times the fact we have 1 mole of nitrogen at 14 grams of nitrogen. That's from the periodic table. Setting it up as a dimensional analysis problem, grams of nitrogen are going to cancel, and once I divide the 0.522 grams by 14, I got 0.03728 moles. Of the nitrogen. We'll do the same thing for the 1.49 grams of the oxygen. So 1.49 grams of oxygen. Multiply it by its molar mass, 1 mole of oxygen, 16 grams of oxygen from the periodic table, canceling out the grams of oxygen and dividing the 1.49 by 16, I got 0.09312 moles. Of the oxygen. Now I have the subscripts in the the subscripts in the empirical formula, but we want to make them small whole numbers. So the next thing we need to do is divide through by the smallest number of moles. In this case, we'll divide each of these moles by 0.0372. Dividing this by 0.0372 moles, that obviously gives me a subscript of 1. When you divide this by 0.0372 moles, I'm going to get 2.5. So if we actually put this formula together, what we have right now is we have 1 mole of nitrogen and 2.5 moles of oxygen. Note that that looks kind of silly. We can't leave a fractional subscript there. I need to multiply each of these subscripts so that I get rid of that 0.5 in the oxygen. So if I multiply each of these subscripts by a factor of 2, that will give me N2O5. So now I have an empirical formula that has whole number subscripts. And this is the actual empirical formula of this particular compound, dinitrogen pentoxide. Let's take a look at another more complex example. A sample of a compound of carbon, hydrogen, nitrogen, and oxygen with a mass of 0.612 grams was found to contain 0.1735 grams of carbon, 0.01455 grams of hydrogen, and 0.2024 grams of nitrogen. It has a molecular mass of 129, and I need to calculate both the empirical and molecular formula. Well, the first thing I need to do for this is, again, as in the previous problem, they did not give us the mass amount of the oxygen, but they gave us the total mass. They said the total mass was 0.6216 grams, and they told us that it contained 0.1735 grams of carbon, 0.01455 grams of hydrogen, and 0.2024 grams of nitrogen. If I add all three of the givens together, I get 0.3904 grams, and that's by adding the 0.1735 grams of carbon to the 0.01455 grams of hydrogen and the 0.2024 grams of nitrogen. What I want to do now is subtract that total from the total mass of the compound, which is 0.6216 grams. Subtracting that from the total, that will give me the mass amount of the oxygen, and I got for the oxygen 0.2312 grams of oxygen. So now I have all four of the masses of each of the elements. Again, once you're given the masses, you need to use the molar masses from the periodic table of each of the elements and convert them into moles. And this hopefully will give you whole number subscripts. So starting off with the carbon, the 0.1735 grams of carbon times the fact that 1 mole of carbon is 12.011 grams. When I did this division, I got 0.0144. moles of carbon. Doing the same thing for the hydrogen, given 0.01455 grams of hydrogen, multiplying that by the fact that 1 mole of hydrogen is 1.077 grams of hydrogen. Doing the division, I got for the hydrogen 0.0144. Going on to the nitrogen, we have 0.2024. Grams of nitrogen times 1 mole of nitrogen, 14 grams, and the moles of nitrogen I got were 0.0144 moles of nitrogen. And lastly, taking the 0.2312 grams of oxygen that we previously solved for, 1 mole of oxygen, it's 16 grams of oxygen from the periodic table. And this is a fairly nice problem because clearly the smallest number of moles that we need to divide each of these by is 0.0144. So dividing each of these by 0.0144 moles will give us all subscripts of 1 in our empirical formula, which is very, very serendipitous. So our empirical formula is going to be CHNO. That is what the empirical formula is. Now, how do we get the molecular formula from the empirical formula? Remember that the molecular formula is equal to the empirical formula multiplied by some ratio subscript. So we need to solve for this multiplying constant here, this subscript multiplier. Dividing both sides of this equation by the empirical formula, I can see that N, our multiplier, is going to be equal to the molecular formula divided by the empirical formula. In this case, we're going to use the molecular formula mass divided by the empirical formula mass. The molecular formula mass was given as 129 AMU. If we calculate out the empirical formula mass, CHNO, that will be 12 plus 1 plus 14 plus 16 equals 43 AMU. So that's the empirical formula mass. Dividing the empirical formula into the molecular formula, I get that our multiplier of N is going to be 3, meaning that the molecular formula is going to be C3H3N3O3. And that is the molecular formula, and the CHNO was the empirical formula. I hope you found these examples helpful, and I look forward to making another video for you.